Okay, everybody. We're going to be exploring derivatives of exponential and logarithmic functions. These are some of our last trig derivatives that we're going to be figuring, or sorry, last derivative rules that we're going to be figuring out. So have your foldable ready. We're going to add 4 more rules to our foldable, and we'll have a couple practice problems at the end. So what I'd like to do is to show you where these come from. I could just give you the 4 rules, but let's explore a little bit where these rules are coming from. So let's take a look. Title your notebook 3.9, derivatives of exponential and log functions. And again, there might be times where you might want to pause and rewind here as we're going through, so just make sure you do that. All right, so let's start with the graph of e to the x, simple exponential function. I would please go ahead and graph that on your graphing calculator, e to the x, in either a Zoom 4 or Zoom 6 window. All right. And if I look at that, it kind of seems that the slope of the tangent line at 0 seems to be about 1. So can you use your graphing calculator? So when you're looking at the graph on your graphing calculator, remember we can go to second trace or the calc menu and number 6 dy dx. So then just type in at 0, and it looks like the derivative at 0 is equal to 1. So I'm at the coordinate 0, 1, and the slope is 1. Well, all right. Well, what about at some other points? So if I make a little table, and you can make a table in your notebook too. So what about the derivative at -3? So now second trace, -3, second trace number 6. So I'm at -3, and I get a slope of 0.049787. And the coordinate there would be x is -3 and y is 0.049787. All right. And then if I go and take the derivative, second calc, number 6 at -2, well, I get a slope of 0.135 and a y value of 0.135. Huh, that's interesting. It seems like the slope is the same as whatever the y coordinate is. So if y equals e to the x and the slope is the same as the y coordinate, then what does that mean? Well, that means the derivative of e to the x is itself. All of the slopes of the tangent line on e to the x wind up being the coordinate at that point, the y value at that point. So the derivative of e to the x is e to the x. If you wanted to know a slope on the e to the x function, you just need to know what the y value is at that point. So this is going to be one of our first rules, and I'm going to save putting of what we should put on our foldable here in a second. It's its own derivative. And if I do the chain rule, this is what I'd rather you put onto your foldable, because most of these will be the chain rule. They're never going to ask you what's e to the x's derivative. So the derivative of e to the u is e to the u times du dx. So you get the same function back, but with the extra chain of du dx. So make sure you put d dx of e to the u on the outside and e to the u du dx on the inside. And pause me if I'm going to be going ahead here. So now let's take this and do it for any base instead of just the base of e. So if I take a to the x and I want to take its derivative, well, remember that we can rewrite this as e to the ln of a to the x. E to the x and ln of x are inverses, so if you compose them together, they'll just cancel each other out. So e to the ln of a to the x is just a to the x. It's like square rooting something that's squared. All right, so if I can do that, well, remember we got log laws that say I can bring the power down out in front, so the x comes down out in front. And so here is an e to the u. What's the derivative of e to the u? Well, the derivative is e to the u times the derivative of u. Derivative of x ln of a. Now remember, a is just a number, like 2 to the x, 5 to the x, 3 to the x. So x ln of a is just a number. So what's the derivative of x times a number? Well, it's just going to be that number, ln of a. So what do I have here? E to the x ln of a. Well, e to the x ln of a is just a to the x. That's how we wrote it in the first place. And so I get a to the x ln of a. So if I write this with chain rule, the derivative of a to the u is a to the u ln of a times du dx, whatever the derivative of the inner function is. So this goes on our foldable too. What's on the left goes outside, what's on the right goes on the inside. And again, pause me as I continue more in here, but here are the two rules we have so far. All right, so e to the u and a to the u, pretty simple and straightforward. So the derivative of 5 to the x is 5 to the x ln of 5 times the derivative of x, which is just 1. So let's go on and now let's take a look at ln of x. Now, we could look at it graphically, but we can also rewrite it. How do we rewrite y equals ln of x? Well, that would be e to the y equals x. It's inverse. Well, how do I take the derivative of things that look like this? Well, you take the derivative of the left, you take the derivative of the right, because this is implicit differentiation. That's why we learned that before we do this. So what's the derivative of e to the y? Well, it's e to the y dy dx, according to implicit differentiation. What's the derivative of x? Well, it's just 1 dx, which cancels out. So if I divide that over, the derivative is 1 over e to the y. Now again, we don't like derivatives in terms of y's, we like them in terms of x's. Well, what is e to the x? Well, actually, let me say first, taking the derivative of the ln of x, e to the y, it was simply x from what we had before, so it's 1 over x. So therefore, the derivative of the ln of u is simply 1 over u du dx using the chain rule. So that's my third one. Pause and put that one on your foldable. We got one more to go. All right, so in this case, we're going to use a little trick in doing the log. In this case, if I don't have a subscript, remember this is the common log, so log base 10 of x. So I'm taking the derivative now, doing the change of base formula. You might have hopefully talked about this back in accelerated trig pre-calc. So I can change this to the ln of x over the ln of whatever the base is. In this case, it was a base of 10. And now I could take the derivative of this using quotient rule, but remember ln of x is, or sorry, ln of 10 is simply a constant. So really this can also be looked at as just leave the constant alone, 1 over ln of 10, that's a number, and just times the derivative of the ln of x, which is just 1 over x that we just talked about. So I get 1 over the ln of 10 times 1 over x. So if I generalize that with any other base, so the log base a of u is 1 over u, that was the 1 over x, ln of a, ln of 10 that I had before, du dx. A lot of times people say it's 1 over ulna, ulna, uln of a, du dx. So let's put them all together here. So here are 4, make sure you get the log base a of u onto your foldable as well. Again, pause me because then I'm going to give you a couple practice problems. All right, so now that you have those 4, what I want you to do is apply the chain rule here to each one of these. So in a second, pause me, jot these down in your notebook, use your new 4 derivatives. Now there's some chain rule inside of here, so be careful, and there might be chain rule within chain rule. So be careful. So go ahead and pause me, and then when you turn me back on, I will have the solutions ready for you. So here we go. The derivative of e to the u is e to the u du. Derivative of 3x squared is just 6x. The derivative of 5 to the u is 5 to the u ln of 5, the ln of a to the x ln of a, du. Now the derivative of the sine of x squared, be careful, x is being squared, not the sine of x. So it's cosine of x squared times an extra 2x. So the whole problem, the a to the 5 to the sine of x squared, that's a u substitution problem, but it's a u substitution within a u substitution. So be careful. The derivative of the ln of u is 1 over u du dx, so 1 over secant of x to the 5th times the derivative of secant of x to the 5th. The derivative of secant is secant tangent, secant x to the 5th, tangent x to the 5th, times the derivative of the function on the inside, 5x to the 4th. And last one, log base 2 of tan of x. Log base a of u is 1 over u ln of a, so 1 over tan x ln of 2 times the derivative of tangent, which is secant squared. So yeah, we're going to have to commit these to memory and evaluating them. And so there's some practice problems to take a look at. So make sure you got your foldable and start committing these to memory. We'll have a quiz on them sometime soon. All right.